Hello, I will discuss analytical animations, new views on physics. We see an animation in the center panel. In order to really understand this, I found I had to surround it with 5 other graphs. 3 of the graphs are complex planes of Tx, Ty, and Tz. I also found it useful to create a superposition of all possible states, the sort of thing that happens with the wave function of quantum mechanics. And then it was fun to look at random samplings from all possible states, something that also happens in quantum mechanics. So this topic begins with Rene Descartes' pictures of math using analytical geometry. We have an expression for a polynomial down there, which is a pretty abstract notion. It seems more concrete when we create this graph. In fact, we can visually pick out important characteristics of the polynomial based on the picture itself. We have more brain power devoted to visual analysis, and that's the underlying power of analytical geometry. It's tie into our visual system. But to bring this into physics, we need to consider Newton's time that is separate from space. Time is absolute, space is absolute. And that was a very productive worldview. But it was Einstein who challenged this notion that time can in fact mix with space. He did this in 2 different ways. The first way was in 1905 with the development of special relativity. There, different inertial observers would see effects based on the differences in their speed. Then in 1915, Einstein was able to generalize the situation to apply to any observer moving in any way. The problem with general relativity is the mathematics behind it is extremely complicated and difficult to apply. And there are only very few situations where anything can really be done productively. Those have been successful, but we have our mathematical limits. What I'm trying to do is make sure that time and space always play together. You might say I'm very anti-Newtonian here. And here is how we do it in the nuts and bolts kind of way using a computer. There's a type of number known as a quaternion, and these are events in space-time. They are 4 numbers that you can add, subtract, multiply, or divide. Now what we do is we make many events, either randomly or in a straight line. And we do some math, take a sine, or calculate that polynomial. We sort by time, and then we animate. And in this screen here, we see how it's done at the command line. There's a function called qrandom n, and I just say make 10 of them, or constant linear motion, which will create 10 quaternions from one place to another. And there are many different sorts of functions I have out there to work with. I take something moving in a constant way, I pipe it into a hyperbolic cosine, I sort that in time, and then what I do is I take this this function, this sorted information, and I put it in a program called QGraph, and that will now create this image, and which takes it about 5 minutes or so. So here is one of the animations created in that process, and we can see that quaternion addition is an inertial observer. And this is that animation that started out this discussion. This thing is moving in a constant velocity, and it's amazing to me that the simplest math act you can do addition is tied into one of the deeper topics in physics, special relativity. Now we're going to animate a sine function, and we're going to see that it has actually several types of symmetry. We have the sine t for the first position, sine t for the x position. Now we have sine t over 2 for the y position. What that does is it means that it will take it 4 pi times 4 pi radians to get around to back to where it started in the y direction, where it will only take 2 pi to get back to its proper spot in the t, x, and z directions. And so this has spin 1 and spin 2 symmetry. And my sense is that this is the way we can do supersymmetry without needing all kinds of new math. If we do old math correctly, there may be more doors available than we currently consider possible. So now we're going to think about the symmetries that are involved in the standard model. One of the symmetries is known as U1. It applies to the photon, and we know what it looks like. It looks like a circle in a complex plane. Now, since we have 3 complex planes, it's a little tilted. The math is pretty simple. We just take a quaternion, we normalize it to itself, and take n powers of it. I really like the superposition of all states because it looks about as straight line as possible. The circle comes about because of time's relationship to space. And so really what's changing here is the velocity. So it flies apart and it gets to the maximum and slows way down, and then it speeds up and crashes together. Now the next symmetry in the standard model applies to W or Z particles, and it has SU2 symmetry. And it looks just like this animation, but I believe I'm the only person who has it on their iPod. Now the math for this is taking the exponential of a quaternion and subtracting its conjugate. And I like to call this Mrs. Pac-Man in 3D because what it does is it springs into life and grows and then consumes itself. I was completely surprised by this animation, and I honestly don't kind of get how it's connected to beta decay, but I do know that I was using the right math. I do know I created about 50,000 quaternions to make this animation, and I do believe it's connected to how nature works, and I've got to do more work to understand it better. But we continue this process by considering a gluon, which has SU3 symmetry, and this looks like an expanding and contracting popcorn ball. As you can see, the math is a combination of the last 2 slides. We've got the U1 there and the SU2, and we take a conjugate and we do the same thing again, and we just take n of those and we end up with this sort of animation. And what's particularly satisfying about this is it almost suggests why we have the standard model. If you see an event in space-time, then it will be somewhere on this sort of expanding and contracting sphere. And so this might actually justify why the standard model, and specifically the groups U1, SU2, and SU3, are the symmetries of the standard model, which would be a very deep insight. It would also be somewhat controversial because the model is actually smaller than the symmetries we usually discuss. So now we go to gamma matrices, which are tools used in quantum field theory calculations. And it looks like the very first one, except I don't think we went right through the origin. I think we did go through the origin last time. This time we're just a little bit off. Now, quantum field theory is a very difficult topic, and gamma matrices are part of the machinery of that very difficult process, and it's hard to understand what the heck it is doing. Now, somebody else pointed out to me that you could do all the work of these 16 gamma matrices by forming a quaternion triple product, where before a quaternion you multiplied it by, say, I, and after it you multiplied it by j. And since there are 4 basis vectors, you've got 4 on the front, 4 on the back, there's 16 possibilities. Now, if we take this one path and we take all the possible 16 different the triple products, this is what you end up with. And you can see kind of 4 clusters of 4 moving throughout the space-time. And if you look at what happens algebraically, the number that's in the t spot and the x spot and the y spot and the z spot, they all shuffle around. So it's whereas the yellow one is the t, x, y, and z, the t then goes into the y spot, the y goes into the x spot, the z goes... it's really strange to see, but apparently quantum field theory says I want to look at all possible ways of using the 4 numbers that happen to be in the calculation. And now we can appreciate why quantum field theory is so difficult. It involves shuffling all of these things around and then calculating the averages of all this stuff so we can say on average what actually happens. So we went through some animations today. We started with the very simplest, addition, and we quickly got into complicated things like supersymmetry, like new views on the standard model, and on some insight into a very difficult topic, the gamma matrices of quantum field theory. So hopefully this demonstrates to you that quaternions can open new doors by making analytical animations. Thank you very much.